Hi everyone, just letting you know that this session's running a little late. We're going to start at 6:15, so thanks for being patient.
Great. Good evening, everyone. So we're going to start. And we first going to start with Pam Pearson, which is the director of ICNet, responsible of the Cryosphere Pavilion. And she will present you a work. No, I'm sorry. I think she will, yeah, she will introduce what she's going to present.
Thank you, Ugo. Um, and thank you for coming to this event at the end of a long day. The primary purpose of this event is actually to recognize and talk about the inevitable loss of Arctic summer multi-year sea ice. If you go through this pavilion, for those of you who are physically here, and especially if you've been at the pavilions that we had at COP25 and COP26, you'll recall that there are 5 standing toblers. This year we only have 4. And then one of them is at the back of the pavilion and is on its side almost. It is toppling or almost toppled. And this decision was made in concert with Arctic sea ice scientists and with their approval. And it's because this loss is now inevitable. We're emphasizing that while the loss is inevitable at least once and most likely before 2050, there's still 4 of these toblers or totems still standing. There's still 4 uh, cryosphere dynamics that we see and still have a chance to prevent tipping in the same way. But we've lost summer Arctic sea ice, even with very low emissions. You'll hear more about that later. But I wanted to begin by going through the overall conclusions of the 2022 State of the Cryosphere Report, which was released here at COP27 about exactly a week ago, actually, at this time. Okay. This is actually the Arctic sea ice slide. And as you can see, I might, if you could run the microphone to me because I've got to be able to see what I'm presenting. Thanks. On? Great. Okay. So you're going to hear more about Arctic sea ice later, so I'm not going to dwell on this slide. But we are updating some of the findings of the 2021 report. And one of the findings has been that the recovery of Arctic sea ice, if we're able to bring temperatures down again, will not be immediate. There will be a decades, centuries long lag that is entirely dependent on how high we allow ocean temperatures to go. If we're able to stay below 2 degrees in particular, we should be able to bring Arctic sea ice back fairly quickly. Otherwise, there may be quite a delay because the ocean has warmed. Mountain glaciers and snow. Glacier loss, and people don't think about this, is essentially irreversible. It takes only a few decades to a century, perhaps, to lose a glacier, but it might take thousands of years to grow it back because the regrowth is very, very slow. This is a picture of the Great Aletsch Glacier from a paper that was released just a couple of months ago. And you can see here on the left, your right, or your left, 2017, glacier extend. With high emissions, the glacier is essentially gone. There's just a little bit left at the very highest altitude. But if we can stay with low emissions, as you can see, most of the glacier, at least at the higher elevations, will be left. So there really is a difference. We're making a choice in terms of preservation of these glaciers. And in 2022, one of the important findings, or the really shocking findings, was that in 1 year, 6% of alpine ice was lost. So a single season, 6% of the remaining ice. And this shows this graphically. And again, in all emission scenarios, we're in a very, very steep glacier loss now. That is because of heat built into the system already over the past century or so. So that can't be halted. But if you look beyond 2100, that's when you start to see a difference between low emissions, medium emissions, and high emissions. So, for example, in Scandinavia, with high and even medium emissions, almost all the ice would be gone. But if we're able to follow a low emission scenario, 20% of the ice that was present at the beginning of this century can still be preserved. And then it's much easier to grow it back. The other thing that I would note is, and you'll see these on the graphs, this is Central Europe, in other words, the Alps. And as you can see, there's actually a slight upwards trend. And that shows two things. There's a very big difference between these different emission scenarios, but it's also the case, as you can see, that's a really, really slow regrowth. It sort of begins well into the 2100s. But it's really slow. It goes from about 40% of where we were in 2000, and by 2300 you reach 50%. So this is 4 or 5% a year that we're able to grow. So it's a very, very slow progression. Possible, not entirely irreversible, but on any human time scale, we're really looking at thousands of years just to get back to where we are today. Polar oceans is something that we really focus on, and it's something that gets nowhere near enough attention because these cold waters, for a variety of chemical reasons, absorb CO2 much more quickly than the mid-latitude oceans. And we're already seeing shell damage today in parts of the Arctic and parts of the Southern Ocean. You see these shells with some damage. This is from the field. This is not from the lab. And you can see that even with very low emissions, there is quite a bit of acidification. So these are waters where shell-building animals probably will not be able to reproduce or survive. But with high emissions, the entirety of the Arctic, the entirety of the Southern Ocean, and even places like the North Sea and the Baltic will have these conditions. And in 2022, some of the observations were that this was occurring faster than previously forecast. And there was also a population crash in the Bering Strait of the snow crab population that was probably due to warming more than anything else, but it's hard to attribute it. But that was an unexpected finding. On permafrost, we had the first documented rise in methane emissions from a permafrost observation site this year that was in Siberia. Size of emissions depends on peak temperature, and permafrost is something that will continue to emit CO2 and methane for a couple of centuries after thaw. So what that means is that even once human emissions are taken down to zero, we're going to need to offset the emissions from permafrost that we're setting in train today. And so that is a matter really of intergenerational justice. And finally, there were a lot of findings on sea ice this year. East Antarctica was found to be very vulnerable to sea level rise above even 1.8 degrees, so below 2 degrees. It really shows how important the 1.5 degree limit is. This is because there are certain portions of East Antarctica that are marine based, they're on water, as you can see in this second slide. And so those can really collapse. And you'll hear in coming days from the author of the East Antarctica paper, who is here, and also on Jason Box, who works quite a bit with the Arctic Council on Greenland and its committed sea level rise. And we're looking at committed sea level rise from Greenland now that is higher than the median estimate of the IPCC. And this is based actually on observations of Greenland's behavior. So these two very important papers both came out in August of this past year and represent an important update. And this is what sea level rise looks like in the Nile Delta. 1 meter, this is 3 meters of sea level rise, which we actually could see by the end of this century, based on some of the projections we're finding right now. This is 6 meters sea level rise, which we could reach by 2150 or 2200 with continued high emissions. And this is 10 meters, and this essentially wipes out the really important breadbasket of Egypt. So my point in showing this slide, other than that we're at COP27 in the country of Egypt, is that cryosphere is important even for countries that are very, very far away from the poles or from mountain regions. It has an impact. Finally, I just want to end by saying that, we still have a choice here. There's still the possibility to avoid this if we follow a very low or low emissions pathway, which means 50%, very stringent reductions before 2030, which unfortunately we're on track for about a 10% growth by 2030. Reaching net zero by 2050, and then negative emissions, which of course are rather difficult to be sure we can even implement in the second half of the century. Here at COP27, we're trying to bring this cryosphere science into all of these various negotiating tracks because it has implications for the urgency of mitigation, how much we can delay or even if we can delay, the importance of the 1.5 goal of really treating that like a guardrail, right? It's something we need to bounce off of. It's not something we can go to and then stay at for as long as we wish, because at 1.5 degrees, we know that the Earth in the past had about 6 to 9 meters of sea level rise. So 1.5 degrees from a cryosphere science point of view is actually not safe. It's important in the global stock take, on adaptation, on loss and damage, really cross-cutting on all the issues being addressed at this COP. So with that, I'd encourage you to look at the State of the Cryosphere report. We have QR codes here, and we also have paper copies for those who wish. But now I'd like to turn it over for the main focus of this event, which is Arctic sea ice. And Dr. Robbie Mallett is here to talk to you about the implications of 1.5 degrees for sea ice. So.
So here is that State of the Cryosphere report. Do pick one up if you'd like to read it. Yeah, I'm going to talk about sea ice, which is the focus of these upstanding toblers, these pillars that we have here, because this year we've really been thinking about the future of Arctic sea ice, and particularly the future that will include missing sea ice, basically, in the Arctic in September when it shrinks to its annual minimum. And I'm just going to talk about where we are now, and also where we are going to, where we have to go, but also what choice we have in where that is, if any. So this is my favorite figure in the whole IPCC recent sixth assessment report. It's 3,950 pages, and they put literally the best figure on like page 10. So they blew their best stuff almost immediately. And climate scientists can really get bogged down in these scenarios and these pathways and what are we doing, emission or concentrations pathways. It all gets super technical, but this figure is the best because it just says the more cumulative carbon dioxide you put into the atmosphere on that x-axis, that sideways axis, the warmer the globe gets. It's super simple, and it's a really straight line. And then the different colors of these different emissions pathways, and it shows that really the only difference between these emissions pathways is when like the total amount of carbon dioxide that you put into the atmosphere. So I want you to remember that this straight line is just more carbon, more heat in the atmosphere, global warming. And this is the result of that experiment so far. So we've warmed the globe by about 1.2 degrees Celsius on average. something like that. It's been happening in kind of straight line over this period, so since about 1980, and it's been warming at about 0.2 degrees per decade in this period that's on the graph now. But because of lots of physics-based reasons, the Arctic warms much faster. The Arctic warms about 3 to 4 times faster. So if we plot the Arctic line on top of the global average line, we see a really radical increase in temperature over the last 40 years. And that's happening at about 0.67, call it 0.7 degrees per decade in this period. And there's a bunch of physics. We often focus on the top one. So we focus on as the sea ice recedes in the Arctic, it opens up an ocean that's very dark and it absorbs the sunlight. It gets super warm. But there are a bunch of other things that actually contribute perhaps equally as much as that really simple, we call it the ice albedo feedback. So I'm not going to go through them because they get quite technical. But I'm just going to say that clouds are also really important. We're changing the cloud regime in the Arctic. We're changing the vertical temperature structure of the atmosphere in the Arctic. We're changing how much heat makes it up from lower latitudes. It just gets pushed up into the Arctic. So it's more than just ice receding. It's a fundamental change that we're driving in the very nature of the Arctic, both in the ocean and the ice and the atmosphere. And a recent one, I'm just going to touch on biology at the bottom. So there have been some recent studies that have looked at how we're greening the Arctic as we warm it, and how trees are actually might be reducing the albedo, and also how phytoplankton in the water might be reducing the albedo. So as well as the physical processes of the Arctic, we're also changing its biology, which is potentially driving a really nasty feedback. And as the Arctic gets warmer, the temperature cranks up decade by decade. The sea ice extent starts to decline. So on the right, you can see the annual minimum extent. That's the area covered by the sea ice in the Arctic. And it's gone down in a very straight line. It's gone down in a really simple way, decade by decade, in response to temperatures, which are in turn a response to carbon dioxide. So this is where it's retreated from over what we call the observational period, the last 40 years. And those dark brown colors, they just represent where the ice used to be and where it's not anymore. And you can see there's a very characteristic pattern, kind of in a ring around the North Pole, up around Alaska in the top left of the Arctic Ocean. And then it just goes around the Siberian coast. And as it pulls away from the coast, that's actually really dangerous, because previously the ice would make it all the way to the coastline, and then it would just be continuous with the land and there'd be no open water. But as it peels back away from the land, the fact that there's ocean exposed there, it makes the environment really sensitive. It absorbs sunlight, and basically for kind of a bunch of really interesting reasons, it turns out the ice edge, the length of that ice edge, really defines how sensitive the ice pack is to warming. So since it's receded from around the land, that's a particularly bad way of it receding, in fact. As well as receding in area, it's also thin. So this pink area is kind of the parts of the Arctic that we've been able to observe the thickness of the sea ice since 2002. The blank bit in the middle, we've had less good eyes on. We've only had eyes on that since about 2010. But looking at where we've had a nice long record since 2002, we can see there's also quite a clear signature of thinning, as well as aerial retreat. And this combination of thinning and also spatial retreat, since the 50s or so, we've seen about a halving of the area and also a halving of the thinning, we think, which results in about a reduction in the total volume, the total mass of ice, by about a factor of 4. So these reductions in spatial extent and thickness act in concert to reduce the resilience of the ice pack in many ways. And that's also true not just for the annual minimum, but also for the annual maximum. I always think it's striking how similar those two downward lines are. And finally, it's just not just about the amount of ice, it's also the type of ice. We've got lots of good reasons to care about that. So older ice, as I'm going to come on to later, that has very special properties. It's thicker, it has a deeper snow cover. it's rougher. It's very physically distinct from the seasonal ice, that temporary ice that's come to dominate the Arctic recently. And that distinction, it's environmentally important, and we're losing it. So you can see that at the beginning of the Ice Age record, we have more than half of the Arctic covered by multi-year ice rather than first-year ice on the 1st of January. And in recent years, it's been much more like a third. So we've seen a clear reduction that's actually come in a couple of step changes as well. So it's not just about melting, but it's also about a physical loss of ice. Sometimes it just falls out of the Arctic through the east coast of Greenland. And we've had at least 2 really serious step changes in the age of the ice in the Arctic Ocean. Just a quick look at Antarctica as well. This is mostly focused on the Arctic, but I do want to say that we're seeing some really exceptional conditions in the southern hemisphere as well for the sea ice. So this year we saw record low minimum extent in Antarctica, really quite shocking. And at the moment we're still tracking the lowest Antarctic sea ice extent on record for the date. So it's been a record year, but it's also been a record week. Antarctica, I'm just going to quickly say why Antarctica is not the topic of this talk. It's very, very difficult to project the future of Antarctic sea ice for a bunch of reasons, and I'll just summarize them now. So the Arctic is an ocean that's surrounded by land, whereas Antarctica is a piece of land that's surrounded by ocean. And that means it's really, really driven by the oceanography, which makes it incredibly complicated, basically, because it's sensitive to upwelling warm water and brine rejection from the sea ice. And the oceanography makes it very difficult to forecast over the next 80 years, whereas for Arctic sea ice, it's much easier. And we also have much better observations in the Arctic. So in the Arctic, we know much more about the snow cover, which really helps us sense what's going on from space. We can look through the snow cover when we know what it is. Whereas in Antarctica, it's much more difficult to subtract the effect of snow on our satellite estimates. And also, I should add that Antarctica is controlled by scary global climate phenomena like El Nino, whereas the Arctic is much more responsive to CO2 concentrations and global temperatures. And there's a little quote here from the IPCC just summarizing why Antarctica is so difficult. We've got limited observations, really large disagreement between these complex global climate models, unresolved physical processes, and temporal and spatial remote linkages. So that's like lagged correlations from a season ago and remote linkages like El Nino and the Pacific Decadal Oscillation and stuff like that. So I'm going to focus back on Northern Hemisphere sea ice now. So this is where we're going to go. This is where the IPCC class models, the best ones we have, say we're going to go. And you can see that you've got the observations on the left-hand side, this black line, and it splits as we move into the future. So the light blue and the dark blue lines at the top, SSP1, 1.5, SSP1, 2.6. That basically, the lower the number, the less global warming we're talking about. That's a simple translation of what those are. So you can see that by emitting less carbon dioxide, by emitting less greenhouse gases, we control the future of the Arctic. So you can see that, and this is the big finding of the report that we've put out, the state of the cryosphere, that no matter what the emission scenario, in the immediate short term, we just are going to continue to see reductions in sea ice extent. So there is no, in all of these IPCC scenarios that you're looking at on this plot, in the next 20 years, it continues to decline. So that's a really important message. But at the end of the century, in 2100, we have a very clearly delineated set of options for our species and for our environment. So for lower emission scenarios, for lower emissions pathways, we end up with much more sea ice at the end. And if you look at the actual values, it's easily a factor of 2. It's potentially a factor of 4 in terms of the area that's going to be covered by sea ice in September. And then I'll just draw your attention to this dashed line. That's at 1 million square kilometers. That's the conventional limit for what we call an ice-free Arctic. The Arctic is mostly an ocean, but it's also a whole bunch of fjords and small inlets that will retain their sea ice through a very high amount of global warming. So we tend to say once we drop below 1 million square kilometers, that's a reasonable definition of being ice free, because there are some coastal environments that for kind of tedious reasons just hold on to that ice. So this is our definition of ice free. Here are some key statements for this 2019 report. It says SROC, that's the Special Report on Oceans and Cryosphere in a Changing Climate. Don't ask me why there's not 3 C's up there. There should be, but they just kept the 2 at the IPCC. Reductions in sea ice extent scale linearly with both global temperatures and cumulative CO2 emissions. So this is where I want you to think back to that first plot that I showed. It scales linearly with both temperature and CO2 emissions. That's because CO2 emissions and temperature scale linearly with each other in this plot. So when we're talking about CO2, we're talking about temperature. And when we're talking about temperature, we're talking about CO2. It scales linearly. So if we put out twice as much carbon dioxide cumulatively, then we're gonna halve the sea ice extent. So the science, we often say the science is clear, but also the science is incredibly simple here. And then talking about the end of the century, for stabilized global warming of 1.5 C, that's the Paris aspirational target, sea ice in September is likely to be present at the end of the century with a 1% of individual ice-free years. At 2 degrees, that's 10 to 35%. So looking at the best model uncertainty, we're looking at 1 in every 10 for 2 degrees. And looking at the worst model uncertainty, we're looking at 1 in every 3 ice-free summers there. But a more recent work looked at higher temperatures, and it spelled it out. So at 3 degrees warming, as we crank up the thermostat, the Arctic is practically sea ice free in September in most years, with longer practically sea ice free periods at higher warming levels. So it's not just at 3 degrees C that we see ice free Septembers in most years. It's that ice free period actually gets longer and more sustained. That's more energy pumped into the Arctic Ocean. That's more disruption on primary producers and more stress on the higher ecosystems. So here's the plots. Here's the good stuff. It looks a bit intimidating, but I would encourage you just to focus on how similar, first of all, these graphs are. So one of them tells us about what happens when we turn the temperature up. The other one tells us what happens when we turn the CO2 up. And the other one tells us what's going to happen over time under 3 different scenarios. And it's all kind of similar, right? All the stories are the same. So if we get on the blue track, we basically end up with lower temperatures, lower CO2, and by the end of the century, on the right-hand plot, we see much more sea ice. And I want to draw your attention, this is September. So this is when the sea ice retreats to its annual minimum. This is going to be the annual minimum that we see. But we see a kind of similar story in March, which is when the Arctic's at its annual maximum. So it's not just a niche September interest we're looking at. We're looking at a whole year round of stresses on the ecosystem, stresses on the environment, but also for the whole year there's choices, right? So it's only the right-hand line that in the left-hand 2 plots extends into those dangerous zones, and it's only the red line that drops into those dangerous sea ice areas in March. And we talk a lot about sea ice in September because it's really important in terms of the energy that we pump in to the Arctic Ocean. But in March, it's also really important because that's the energy that comes out of the Arctic Ocean into the atmosphere and warms the atmosphere. So it's a two-way street that in the summer when we see an ice-free Arctic, we're kind of damaging the ocean and we're damaging the ocean ecosystems. But in March, we see that we're really playing havoc with the atmosphere. We're warming the atmosphere, and we're not growing enough sea ice in the winter. So there's a year-round spectrum of sea ice damage that we see under these high emission scenarios. So these are the key findings of the IPCC for low emissions scenarios. So as I've said, it responds directly. The technical term will be linearly to our emissions. So you get out what you put in. But also for 1.5, 2 degrees, 3 degrees, it's not committed beyond our emissions. So we do actually have quite a lot of control over the future that we see. We don't get runaway scenarios for low and even medium emission scenarios. And the sea ice loss is actually very reversible. So there are a number of really, really good reasons not to overshoot 1.5, particularly for the land ice. You see committed losses of land ice that are multi-centennial, so hundreds of years. The same with permafrost. But for sea ice, if we overshoot, we do actually see no hysteresis, is the technical IPCC term, but that basically means it's reversible. So if we go back down to maybe 1 degrees or even 0 degrees, that's a question of governance, how far back down we go. We do actually recover the Arctic sea ice both in summer and in winter under low and medium emission scenarios. So that's all I've got to say. If anyone's got any questions, please do go ahead. I'm happy to take questions on what's in the slides or Arctic climate science in general. And I would definitely encourage you to pick up one of these reports. The State of the Cryosphere 2022, there's loads of really good info and plots in there. Thanks. It looks like there are no questions. Okay.
Thank you. And I'll say we have a wonderful cultural evening event that is planned to begin at about 7:30 or perhaps a bit earlier by our former early career scientist volunteer, Jimena Aguilar, who is going to be now taking over the pavilion a bit, putting up some artwork, and it will involve poetry. And I'm not quite sure what else, but it's going to be exciting. So we're really looking forward to this. Thank you very much for attending.